Situations may arise in which a battery or a battery bank is to be charged by a solar panel or a combination of solar panels, depending on the capacity of the battery or the battery bank to be charged. So this video is all about battery charging by solar panels. If you have not subscribed to my JK Multimedia Solutions channel, please do so as I move on with this video. Thank you. Now, moving on. Here is the schematic diagram or the wiring diagram of how to charge a battery or a battery bank by solar panel or a combination of solar panels depending on the capacity of the battery or the battery bank to be charged. So here we have the sun with sun rays falling on the solar panels. Then from the solar panels we go to the solar terminal of the MPPT charge controller, and from the battery terminal of the MPPT charge controller we go to the battery as clearly shown here. MPPT means maximum power point tracking. So we have maximum power point tracking charge controller. So as usual, I'm going to use some illustration to explain the concept. Please do follow me in this video. Now, the illustrations. Number 1, a 12 volt 200 ampere hour lithium ion phosphate battery has been discharged by 80%, meaning that 80% of the battery capacity has been used, remaining 20%. Now the question is, calculate the number of solar panels of a particular rating that will be required to charge the battery fully. Sunshine time is equal to 5 hours. B. Hence or otherwise determine the rating of the MPPT solar charge controller that will be needed. Number 2. A 48 volt battery bank comprises 2 battery strings in parallel. Each string contains 4 number 12 volt 200 ampere hour lithium ion phosphate batteries in series. The battery bank has been discharged by 80%. Calculate the number, that is A, calculate the number of solar panels of a particular rating that will be required to charge the battery bank fully at 5 hours sunshine. B. Determine the rating of the MPPT solar charge controller that will be required. Those are the questions. Now, solutions to the problems. 1A. Battery 1 is equal to 1 number 12 volts 200 ampere hour lithium ion phosphate battery. DOD, that is depth of discharge, is equal to 80%. That is 80% has been used. Sunshine time is equal to 5 hours. Then total battery watt hour is equal to 200 ampere hour multiplied by 12 volt. That is 2400. Watt hour to be returned to the battery is equal to 80% of the total capacity in watt hour, and that is equal to 1920 watt hour. Amount of power required in 5 hours sunshine is equal to 384 watts. Let 150 watts 22.5 volts open circuit voltage 8.33 ampere maximum power current or current at maximum power 18 volts voltage at maximum power, and 9 ampere short-circuit current, monocrystalline solar panel be selected. That is the selection of the panel, solar panel. Then number of 150 watt solar panels required is equal to 2.5, which is approximately 3 number. So hence 3 times 150 watts is equal to 450 watts is equal to actual power required. Therefore, total solar panel array power is equal to 450 watts, and let the 3 number 150 watt solar panels be connected in series. So the answer to the A part is 3 number 150 watt monocrystalline solar panel with all these parameters. So, and they are to be connected in series as shown here. So, and then we have the output of the solar panels going to the MPPT solar charge controller. MPPT means maximum power point tracking. So if you multiply 22.5 VOC by 3, you get 67.5 VOC. That is open circuit voltage of the array now. So then the 450 is obtained by multiplying 150, that is the wattage of each of the solar panels, by multiplying the 3 by 150, you now get 450, and that is what we have going to this going to the charge MPPT charge controller. If you divide the total wattage, which is 450 watts, by 18 times 3, you have 8.33 ampere. In other words, the current flowing in the 3 solar panels, the current is the same. It's the same current. The same current and the same current, since they are in series. Now, solution 1b, battery charging current is equal to this. One thing with MPPT charge controller is that it behaves like a transformer. The power on the solar panel side is equal to the panel on the battery charging side, 450, as we calculated earlier. So, and this is the open circuit voltage total for the solar panel array. Now, then MPPT charge controller require to have input solar voltage, that is the input terminal from the solar panel. The voltage is this as calculated earlier. This is the open circuit voltage of this solar panel array. So the charge controller, the input of the solar side should be greater than the open circuit voltage of the solar panel array, which is 67.5, and battery charging current should also be greater than 37.5 ampere. So we cannot just choose the exact value. So filtering energy 100/50 is suitable, since it has 100 volts PV input voltage and battery charging current of 50 ampere. So 100 is greater than the open circuit voltage of the solar panel array, and then 50 ampere is also greater than the charging current. Okay, the battery charging current in this situation. And that is the end of question 1, or solution to question 1. Solution to 2a, question 2a. So 48 volts battery bank with 2 parallel strings. Each string has 4 number 12 volt 200 ampere hour batteries in series, and this is the battery bank. So each of this is one battery, another one. These are the two strings, 1, 2, and then 4 batteries per string, and then we have each of them rated 12 volts, 200 ampere hour. That's the battery. So we now have all these ones in series, and the two strings are connected in parallel. So the two, that's why you will have this one going to the MPPT charge controller. Alright, just as we have it here. This is MPPT charge controller. There is a connection between the battery and the MPPT charge controller. In this case, instead of ordinary battery, one battery, we are having a battery bank that is comprising of many batteries. So battery bank capacity now is equal to 48 volts, because we have 12 volt, 12, 12, 12 volt, 12 volts. That's 12 times 4, 48. So this also 48. So when they are in parallel, the resultant voltage is 48. Alright, and the capacity in this case, each string will have 200, 200, 200, 200, 200, because when batteries are connected in series, the ampere hour does not change. It remains constant. It's only the voltage that increases. So we have 200 ampere hour in parallel with another 200 ampere hour, making 400 ampere hour, and that is what is here. So total battery watt hour is equal to this. So DOD, that is depth of discharge, is 80%. The battery bank has been discharged by 80%, remaining 20%. Therefore, watt hour to be provided, that is to be returned to the battery to charge it fully, is equal to, that is the battery bank, is equal to 80% of this, and that one will be this one, 15,360 watt hour. Then given 5 hours sunshine, we can calculate the actual wattage by dividing the watt hour by the sunshine time, and that is 3072 watt. 2a continues. That is the solution. Let 400 watt 49.7 VOC, 9.6 IMP, 41.7 VMP, 13.73 AISC. ISC means short-circuit current. VMP means voltage at maximum power. This one means, IMC means current at maximum power. And then VOC means open circuit voltage. So let this solar panel, which is 400 watts, let it be selected. Then number of 400 watts, 49.7 VOC monocrystalline solar panel require is equal to this 7.86, which is equal to 8 number approximately. Now actual wattage required is equal to 8 times this. So the solar panel array, we have 2 parallel strings. Each string we have a 400 watt solar panel in series, and this is what we are. This one string having 400 watt so 400 watt solar panels in series. This is another string of 4 solar panels, each having 400 watts, and then we have the connection going to the MPPT charge controller, and that is what we are having here from solar panel. It goes to the MPPT charge controller. From MPPT charge controller, it goes to the battery. So, and that is so the answer to this 2A is that we require 400 watt solar panels to be connected in this one. As I said before, solution to 2A is 8 number 400 watt monocrystalline solar panels. Okay. Now, coming to solution to 2B, I also said before that MPPT charge controller behaves like a transformer. That's why the power on the solar panel side is always equal to the power on the battery charging side. So all the figures here are for solar panel array, not for a single solar panel. Now, let's move on. Battery bank, this is the capacity of the battery bank. It will be, this is correct, this is also correct. Then the charging current now is equal to, that is the battery bank charging current is equal to 32 by this, and it's 67 ampere. So solar panel array open circuit voltage is this, according to what just like we have it here, 49.7. so that is according to the data from the manufacturer. So we calculate it for the array to be this. So the suitable MPP charge controller must have solar panel voltage greater than 198, that is, must be greater than the open circuit voltage of the solar panel array. So, and another thing, and the battery, and also, and the battery bank charging current should be greater than 67 ampere. We should not just take the exact value. It has to be higher slightly. So, featuring energy MPPT charge controller 250 by 100, that is 250 volts, and 100 ampere is therefore suitable. Now, to calculate the sizes of these fuses between the solar panel arrays or solar panels and the MPPT charge controller, we consider the voltage at the maximum power of the solar panel array, which is 4 times 41.7, and use it to divide the total wattage here, which is 3200. The answer will be slightly less than 20, so that makes 20 amp fuse suitable. So 20 amp to 20 amp. So, and between the MPPT charge controller and the battery, we have calculated the charging current to be approximately 67 ampere. So, and the fuse that is very close, the fuse rating that is close to that is 63 ampere. So, and that's why we are having 63 ampere. So, this is how to do the sizing of the fuses. In this situation, the voltage that should be used for the diffusion should be the voltage at the maximum power of the solar array, not the open circuit voltage of the solar array. And that is it. So, if you have not subscribed to my JK Multimedia Solutions channel, please do so, and expect more scientific and more practical engineering videos. Thank you very much.